So this video lesson is about weight and mass. More specifically, it's applying Newton's first, second, and third laws to hanging objects and how your weight can actually change, but of course your mass does not. So just to start off, let it be known that mass cannot change in physics, right? Your mass is set in stone. So if you have a block that has a mass of 10 kilograms, its mass is going to remain at 10 kilograms no matter what. The weight, on the other hand, is of course your force of gravity. So your weight can change depending on whether or not you're in motion. So if you're accelerating up or down or at an angle to the ground, or just even where you are on Earth can actually affect your weight. So weight has its own equation. Weight is your mass multiplied by the acceleration of gravity. And once again, your weight can actually change. If I take a 10 kilogram mass and put it on the moon, it still has a mass of 10 kilograms. If I take a 10 Newton object, so again, the weight measured in Newtons, and put it on the moon, it would be 1/6 that weight. Because you have about 1/6 the gravity on the moon. So, an object's weight is more or less determined, if we're just talking about objects at rest and not having to worry about how weight can change, we are typically talking about the gravitational force field. So we're talking about Earth's acceleration of gravity, which we know that if something is dropped on Earth, it's going to accelerate downwards at a rate of 9.81 meters per second square going down, and we've more or less just called that G. So the units for acceleration are a meter per second square. But if we actually look at the equation for weight, I'll address everything else that's on the screen in a moment. If we look at the equation for weight, you've got your mass multiplied by your acceleration of gravity. So if you manipulate that equation around, your acceleration of gravity is your force divided by your mass, which works out to a Newton divided by a kilogram if we actually just look at the units. And so therefore, a Newton per kilogram is the equivalent of a meter per second square. Except we actually talk about the acceleration of gravity, it really technically is a gravitational force field. But we'll talk about fields in another video on another day. So on Earth, the accepted value on average is 9.81. We like to use 9.81 in my class, newtons per kilogram or meters per second square if you're just doing basic kinematics. The mass of the sun is quite a bit larger than Earth, and so it creates a larger gravitational force field. And so its gravitational field or its acceleration of gravity, again, if you're using just basic kinematics, would be 274 meters per second square or newtons per kilogram. The moon is about 1/6 that of Earth, and so you would weigh a lot less on the actual moon. Okay. So if I combine this knowledge with kinematics, we'll do a quick problem here. It says on Jupiter, a 3 kilogram mass has a weight of 81 newtons. If a 5-gram coin were dropped on Jupiter, how far would it fall in the first second? So this is a kinematics problem that just requires a little bit of weight. So we are given weight and mass. So weight changes. If this was on Earth, this object's weight would be closer to 30 kilograms, or sorry, 30 newtons. Even I mess it up once in a while. But again, we're on Jupiter. So Jupiter's a lot more massive, so it has a lot larger gravitational pull. So start off with your basic weight equation. Your weight, Fg, is equal to your mass times your acceleration of gravity or your gravitational field. Manipulate for your gravitational field, and that is your weight divided by your mass. So all we'd have to do is just take our 80 newtons divided by our 3 kilograms, and we'd end up with a gravitational field strength or your acceleration of gravity of Jupiter to be around 27 meters per second square, approximately. So we need to know this because if we are dropping a coin on Jupiter, if you can imagine standing on the surface of Jupiter, there's a lot wrong with that comment, but just go with me on this. We typically have a free fall problem. So a free fall problem is typically defined by using good old-fashioned kinematics. So the displacement going down is equal to 1/2 your acceleration of gravity multiplied by your time square. And since we know the acceleration of gravity is now 27 meters per second squared at Jupiter, all we have to do is plug that into your kinematics equation. With your 1 second, square that, it becomes 1 squared second, and the units of a second will cancel out, and you've got a simple little 13.5 meters. So it's going to travel a pretty great distance in that 1 second on the surface of Jupiter. So that is just your weight being used to help solve kinematics equations. We can use your weight to solve other types of problems as well. So this would be combining it with Newton's second law and Newton's third law. So here we have two masses. One's on a shelf, one is hanging, and they're connected together by a string. So they're under tension. If mass 2 was allowed to fall, it wouldn't fall freely, it wouldn't be under free fall, but it would accelerate downwards. But because it's attached to a rope or a string or whatever you want to call that thing, it is not going to fall down at a rate of 9.81 meters per second squared. So it's going to have a slightly different weight. We could call it an effective weight because it's not going to experience Earth's full gravitational field strength. It's going to be slowed down by the actual tension. So Newton's third law works like this. The tension on mass 2 is going to be pulling mass 2 upwards. Whereas on the pulley, Newton's third law says it's going to pull down at the exact same rate. So pulleys are great because they will translate a force going downwards into a force going horizontally, left or right. So in this case, the weight, the tension pulling down here is going to be equal to the tension pulling to the left from that perspective. Okay, and then again, Newton's third law, whatever the tension is here in the magenta is going to be equal but opposite to the tension that we see in green on mass 1. So the pulley is great for that because it lets us skip this step altogether, and we can say that the tension here on mass 2 is going to be equal to the tension here, but in a different direction. I want to say equal but opposite directions, but the pulley has made it go from a vertical direction to a horizontal direction. So Newton's third law works with this section here, and then again, the pulley translates it to horizontal, and then we have Newton's third law acting right there again. So we are going to combine Newton's third law. It's just not going to seem like it once we get going. So we need to figure this problem out. Find the tension and the acceleration. So first off, I recommend that we draw a free body diagram. So I would do a free body diagram at mass 1. So again, this was mass 1, this was mass 2. I'll just leave the question in the corner at the top. So the free body diagram at mass 1 is a nice simple free body diagram. It is on a surface, so it has weight. So that is your force of gravity. I'll put 1 next to it. And because it's on a surface, it would have to have a normal force. Okay, but it's on a surface. It's on a shelf. It's not breaking through the shelf. It's not flying off the shelf, at least not yet. After all, this guy hasn't gone down enough yet. So we're going to make the assumption that the two vertical forces cancel each other out, and we're going to ignore them from this point on for mass 1. In other words, all we have here is our force of tension, or the force of mass 2 acting on mass 1. There is only one rope, so I'm just going to call it my tension. Positive direction in this case is going to be to the right. If I include my y, it's going my y direction. It'll also be going up, but in this question, again, I'm just going to ignore the vertical. And then all I really have at this point is my net force in my x direction should be equal to, of course, the sum of the forces in my x direction, which should be equal to mass 1, because that's my free body diagram, times its acceleration. Now there's only one force horizontally, so this one's straightforward. My tension vector should be equal to mass 1, which is 2.0 kilograms times the unknown acceleration. That's all I can do right there because I don't know any other information other than the fact that if I'm going to define to the right as positive, I can remove the vector symbols. So because I know I'm going to the right, I'm just going to write my tension as a positive number. Mass just stays the same. and I can remove the vector notation for my acceleration because I know just by looking at the diagram that mass 2 is going to fall down and it's going to pull mass 1 to the right. So I know I can define to the right as positive. And since there's only one force and one acceleration, Newton's second law says that the acceleration has to be in the same direction as your net force. So I can just stop there. I don't have to worry about vectors at this point. My Ft, my tension, and my accelerations from this point forward are basically scalar values. Okay, because we have determined where the directions are going to go. So then I can actually go down to my second free body diagram. So free body diagrams, again, separate masses. Sometimes they'll combine masses, but often we separate masses. So this is the hanging mass, the 5 kilogram mass. The hanging mass is attached to a rope. So we call that the tension. So again, with Newton's third law, the tension from one guy's perspective has to be equal but opposite to the tension in the other guy's perspective. But the takeaway from that is they're going to be equal in strength. So that means the magnitude for my tension on the hanging mass is going to be the same as the magnitude of tension for the block on the shelf. So we also have weight. So this is going to be the second mass. So I'll call it the weight 2. And those are the only two forces involved. It's a hanging mass. So I'm going to work in the y direction. And I know this thing should be going down if I release the mass from rest. So I'm going to define down as positive. I try to define the actual direction it's going to accelerate as the positive direction. So therefore, my net force in my y direction is going to be equal to the sum of all forces in my y direction, which is going to be equal to mass 2, because again, I'm doing a free body diagram for mass 2 multiplied by its acceleration. Because the two masses are attached together, they will have the exact same acceleration. Later on, if you get advanced in engineering, you'll kind of know why that's wrong. Strings will actually stretch, but we're in fundamental physics, so we assume that nothing stretches. Right? So whatever the tension is whatever the tension is, and therefore everything has the exact same acceleration. Try not to look too far into that this year. So we've got two forces in the y. We've got our tension force, vector, added to our weight, vector, and that's equal to mass 2 times the acceleration. All right, so I could plug in my actual values here. So tension, I've got a relationship for tension. I've already solved for the magnitude of tension. Okay, so what I'm going to do is I'm going to actually just plug that into here. So my tension is actually 2 kilograms times the acceleration. And I'm not putting a vector symbol on the acceleration because I've already dealt with the, what happened there? I've already dealt with the acceleration earlier. So again, I mentioned it once, I'll say it again, from this point on, a while ago, these are both magnitudes, no direction. Unfortunately, I'm in a new question. My screen is playing a dancing game. I'm in a new question, whereas tension over here, it still has the vector symbol on it, so I haven't dealt with the actual direction for tension. So then I look at what I defined as positive and what direction tension's actually going. Tension is going up. I define down as positive, so therefore I have to remember to make this 2 kilograms times the acceleration a negative value. So that takes a bit of practice. You might mess that up once or twice, but after you do enough problems, you'll remember to do that. So my weight, that's something different altogether. So let's add the weight. So my weight here, I'll write the equation off to the side. My weight is mass 2 times the acceleration of gravity. So that is my equation for my weight. So if I plug that into this equation here, it should be 5.0 kilograms multiplied by 9.81 meters per second squared. So that is the equation for my weight, and I leave it as a positive value because, once again, I define down as positive. That should be equal to my 5.0 kilograms. I use 5 kilograms because I'm at mass 2, so that's what goes into my net force equation, multiplied by the acceleration. I define down as positive, and so therefore I can dump the vector symbol because it's pretty obvious that if I have the situation where I have a hanging mass and I release it from rest, well, that hanging mass is going to fall down. Going to drag the mass on the shelf with it. So, do a little bit of math. Okay. From this point forward, what do I have here? 5 times 9.81 meters per second square will give you approximately 49.05. I'm just going to write down 49 newtons. I've got this -2 kilograms times the acceleration on the left-hand side. I've got a 5 kilograms times the acceleration on the right-hand side. So I'm going to move in orange. I'm going to move this 2 kilograms times the acceleration over to the right-hand side. And I'm going to do that by addition. I'm not going to physically write that down, but I will let you know again, since I'm moving a negative over to the right-hand side, I would be adding 2 kilograms times the acceleration to both sides. So that's going to give me 7.0 kilograms times the acceleration. Right? So if I get rid of the 2 times the acceleration on the left-hand side, since it's negative, I'd have to add 2 kilograms times the acceleration to both sides. So that now gives me 7 kilograms times the acceleration on the right, 49 newtons on the left. So just divide both sides by 7.0 kilograms, divide this side by 7.0 kilograms, and you get an approximate acceleration of 7, probably 0.01 or something. I can't remember what I said that 49 was, but 2 significant figures, I would just call it 7 meters. Actually, leave it as a newton per kilogram. That would be good enough. Newtons per kilogram. And that is good enough for the acceleration. If you called it a meter per second square, that is also fine. So you can see the falling object has an acceleration slightly less than 9.81. And that's once again because it's not free falling. If an object is falling, its acceleration should not be greater than 9.81 meters per second square, unless of course it's being pulled down or has a rocket attached to it. Otherwise, nothing's going to fall down faster than gravity. Right? So this makes sense. It's attached to something up top. So part B of the question, well, it's not that it was separated in part A and B, but the question asks for us to find the tension and the acceleration. So we found the acceleration. So that means, oh good, I don't have to move my screen. So that means all we have to do now is put that 7 newtons per kilogram or 7 meters per second square into my tension equation. And I'll just do that off to the side here. I will say that the tension, I'll rewrite the equation because that's looking sloppy, is 2.0 kilograms multiplied by the acceleration. And once again, there's no vector symbols involved. So we're just solving for magnitude. So you take your 2.0 kilograms, multiplied by your 7.0 newtons per kilogram, because I did not convert it into a meter per second square. The kilograms cancel. Your kilograms cancel. 2 times 7. The tension in that string is just 14 newtons. Right? And that's all you have to do for a question like this. I, again, just solve for magnitudes. I never once solve for direction. If I want, I can point out that from the 2 kilograms perspective, it is accelerating at what just happened. Smartboard is not overly smart. From the 2 kilograms perspective, it's accelerating to the right at 7 meters per second square. From the 5 kilograms perspective, it is accelerating downwards at 7 meters per second square. In magnitude, they are both accelerating at 7 meters per second square. Right? As far as forces are concerned, from the 2 kilograms perspective, it has a tension of 14 newtons going to the right. And from the 5 kilograms perspective, it has a tension of 14 newtons pulling it upwards. Okay, so that's really all there is to it. Next question involves elevators and how weight actually changes. So this question is a bit of a mouthful. There's 4 parts. I'll try to make this as painless as I can, but I make no promises. It says a 40-kilogram girl is riding in an elevator while standing on a scale. So here's a picture that I happened to pilfer from the internet. She's standing on a scale. Why she's doing that, I have no idea. It's a physics problem. Don't look into it. Part A says sketch a free body diagram of the girl with all the forces shown. Part B, what is her apparent weight? So the scale reading or the normal force. When the elevator is accelerating upwards at 2 meters per second square, what is her apparent weight when the elevator is accelerating downwards at 2 meters per second square? And when the scale reads 392 newtons, what is / are her motion conditions? So part A is what we'll start with. So part A just says draw the free body diagram. So the free body diagram, this is of the girl. Okay, so I say at girl because I'm not overly proper. So the free body diagram at the girl. What just happened? Why is my pen not working? Free body diagram at the girl. So again, I'm not an artist, so that's a picture of the girl. Oh, I screwed up. She's in a green dress. That's the picture of the girl. There we go. That's better. More accurate. Okay. She is a human, so therefore she has weight. She's standing on a scale on Earth, so therefore she has a force of gravity. She is on a scale, and therefore that scale is going to push back up on her, and therefore that's her normal force. Right? Her normal force is often seen as the apparent weight. That's the weight that you will feel or the weight that you will experience, which is different than your actual weight, which is Earth pulling you down. So the normal force is often what you're measuring when you measure a weight. So part A, free body diagram, that's all there is to it. It doesn't tell us in part A whether it's accelerating up or down. I know that you have different parts of that question. So I'll kind of draw a separate free body diagram for, actually I'll do it on the next page. So for part B, what is her apparent weight? Scale reading when the elevator is accelerating upwards. I will draw a new free body diagram just to kind of point out a difference. So it says that we are accelerating upwards. So that means we have an upward acceleration. So that means I'm going to make upwards positive because we have an upwards acceleration. Our free body diagram is only slightly different. Her weight is technically the same. It is still going to be whatever it's going to be. Okay, mass times acceleration of gravity. Her apparent weight will be a little bit different. Okay, so we're going to have a slightly different weight. If she is accelerating upwards, I know this already, but you'll see when we do the math, that she should have a larger normal force vector. If you don't know that ahead of time, that's fine. You would have just gone to the default. You got a force going up, you got a force going down, that's good enough. But I know a bit more already, so I'm going to work ahead a little bit, and I'll show you how that works out right now. So since we're accelerating upwards, that means my net force, and we are working in the y direction in case you weren't curious. We're working in the y direction only. So my net force in the y direction is equal to the sum of all forces in the y direction, which is going to be equal to her mass times the acceleration of the elevator. So again, free body diagram at girl. So this is the girl's mass in question. So there's two forces only. You have a normal force, which is her apparent weight, plus her weight, her gravitational weight, her weight according to Earth's gravity. Okay. Now, we know enough that we can calculate her weight. That is your mass times your acceleration of gravity. I'll just solve for that separately down below. It said she is a 40-kilogram girl. How many significant figures? Let's assume that was 2. So 2 significant figures. Should have been an underline with the 0, but we're going to call it 2 anyways. Your acceleration of gravity is 9.81 meters per second square, or newtons per kilogram, really whatever you feel like writing down. I'm happy either or. Do a quick little bit of math, and you will probably get something on the line of 392 newtons. Okay, and that's where I'm going to leave that one for now. Yes, the calculator said a bit more, but I technically only have 2 sig figs, but I'm not done, so I'm not going to round that anything more than 392. So we're looking for a normal force. We know weight is going down, so that would be a negative 392 newtons. A That should be equal to 40 kilograms. And the question said that we are accelerating upwards at 2 meters per second squared. So we're going to put in 2 meters per second squared, 0.0, and I'm going to draw into the picture meters per second squared. So I'm not an excellent mathematician, but I'm willing to bet that our normal force, first of all, let's maybe bring this over to the other side and do an addition, such that my normal force is going to be equal to 80 newtons added to 392 newtons. And I will get an approximate normal force to two significant figures of approximately 470. So 472 if I'm actually writing down every digit, but I'm going to just stick with two significant figures because I believe that's what the question was given me. So the scale is going to read her as being heavier than she actually is. So that's how I knew to draw. I knew that ahead of time. That's how I knew to draw my normal force vector to be a little bit longer. If you didn't know that ahead of time, that is perfectly fine. Once again, you could have defaulted back to that free body diagram and I wouldn't be too annoyed. But now that you know more, you should probably recognize it should have been a longer one because my normal force is larger than my actual weight. So that was part B. When you're moving up in an elevator, you're going to feel heavier if you're accelerating. Part C, you probably guessed, since now we are accelerating downwards at 2 meters per second square, our free body diagram of the girl is going to look slightly, oh, I messed up, is going to look slightly different. Green dress, right? So now we are accelerating downwards. Her weight will remain the same because her mass hasn't changed and Earth's gravitational field didn't change. But since she's accelerating downwards, her normal force, the force of the scale pushing back up on her, is not going to be as great. And so therefore, that's going to be a smaller force vector going up. My vector going up is slightly smaller than my vector going down. Right? And again, I know that ahead of time. You will see how that works out mathematically right now. So let's make down positive because that is the direction we are accelerating downwards. So my acceleration is going downwards. So again, I do the exact same thing. My net force is equal to the sum of all forces, which is equal to my mass times my acceleration. And we are again working in the y direction. So I have two forces. I have a normal force added to a weight is equal to her mass times the acceleration. I saw for her weight previously on the last page, I said it was 392 newtons, so that's going to remain the same. All right. But my normal force is different. So in this context, my normal force stays as is. I am going down, so it's now a positive 392 newtons. All right, we're using more or less the same values as before, but I'll write it out different separately. So 40 kilograms multiplied by 2.0 meters per second square. So except this time we're going down, board is jumping. Again, it's jumping. What's going on here? There we go. So this will give us 80. We're adding 392, but we should subtract it to get it to the other side. So we'll subtract it. And our normal force will therefore be 40 times 2 is going to be 80 newtons downward, because down is positive now, minus 392 newtons when I bring it over to the other side. And I solve for a normal force to be 312 newtons. Negative. So that negative means that I'm going downwards. All right. My normal force, 312, is less than my weight. So she's going to feel lighter as the elevator accelerates downwards. Part D says, a 40 kilogram girl is riding on the elevator, standing on a scale. When the scale reads 392 newtons, what is or are her motion conditions? So I'm going to draw one final free body diagram. My board is having trouble keeping up. There we go. Here's my girl in the green dress. She has weight still, and we know her weight is 392 newtons, and she has a normal force. And this time it says when the scale reads 392 newtons. So that means her normal force is also 392 newtons. But it doesn't tell you what the motion conditions are. I don't know if I'm going up. I don't know if I'm going down. I don't know what to define positive. I'm going to be simple and just define up as positive because when in doubt, I say up as positive. So if I go to do my net force, which is the sum of all forces, which is equal to her mass times her acceleration, it doesn't take too much to recognize that when you do go through the motions of writing out the equation, in this context, her normal is 392 newtons going upwards, so I leave it as a positive. Her weight is downwards, so therefore 392 as a negative is equal to, well, her mass times acceleration. I'm not going to bother writing any numbers there because you can clearly see that 392 and negative 392 is going to give me 0. And 0 is equal to mass times acceleration. Well, I can divide by her 40 kilograms, but it's not going to do anything. So we'll just skip that step and say there's no acceleration. So all I can tell you at this point is since there's no acceleration, she could be at rest in the elevator, right? Her velocity could be 0, could be at rest, or she could have a constant velocity. She could be moving up at a constant velocity or a constant speed. I've defined up as positive. She could be going down at a constant speed, otherwise known as a constant velocity. A takeaway here is when your acceleration is 0, you're in a state of inertia. So this is a Newton's first law problem now. So therefore, there is no experiment should be able to do to determine her actual direction of motion if she was truly in a state of uniform motion. She probably knew she pressed up or down, and so therefore she would know which direction she's going, but otherwise she would have no idea, only because there is no acceleration. Okay, so that was a lot for weight and mass. I think I'm going to stop there. You have a handful of weight and mass problems to try. Email me if you have any questions. I believe they probably start on, you know what, I'm not going to say a page number because I forget what page they start on. Go through your notes. It's got a title, weight and mass. If you have a question, please contact me, send me an email, and I'll give you a hand with some of those questions. Okay, have a good one.